I want to cover a few common lab techniques in a chemistry or analytical chemistry lab.
And one of the big next ideas in the class that I want to talk about is this idea of molarity. So making solutions and making dilution. So molarity has something to do with moles, but it's not the same. Molarity is similar to the idea of density, but instead of grams per milliliter, like we were doing with the egg density, we're looking at moles per liter. So the number of moles you have, so the number of moles per liter. And this is the same as density. It's the same concept, except for we're typically, because we're using liters, right, we're in liquid, aqueous solutions typically. Very commonly used in biology labs, in chemistry labs. So if you guys are going to be working in biology labs, you're going to have to make up compounds with certain molar solutions. You can still do, we do the same thing. We usually use a big M for molarity. And like we were talking about, the same with grams and milliliters and all those fun things, we can use those kind of prefixes to do. You can do like a micromolar, nanomolar solution, picomolar solution, usually going smaller, not more concentrated typically. But so you can have this same idea in molarity. Now when we're doing dilutions, we have concentrated, right? You have a really concentrated solution. What could you do? You could pour some of that off, add water, and you're diluting it. So you have a small volume concentrated, you're going to dilute that small volume into a larger volume. The number of moles here doesn't change, right? From one solution to the next. We have the same number of moles if I'm doing a dilution in a compound. When that's the case, when you don't change the number of moles, there is a certain way that you can solve problems. But the problem is sometimes people use that inappropriately. So I'm going to try my best to make sure that you don't do this inappropriately, which is pretty easy. I've seen it a lot. And I'm sure you've seen this equation before. C1V1 equals C2V2. Has anyone who has never seen this before? Anyone? Has everyone seen it then? If you have seen it, raise your hand. Come on, raise your hand. You haven't seen this? Okay. What this means is concentration of number one solution. Or initial. It should actually be initial and final. But a lot of people write it as, so this could be initial and final, would be another way. Because really, this is the initial concentration, and this is the final. The initial concentration of the solution is 1 molar, right? So this is C1. And the volume is initial is V1. That's 500 milliliters in this instance. And whenever we take a solution and take all of that solution and dilute all of that solution, so we don't change the number of moles, we're just changing how much solvent is associated. That will equal C2V2. So I take 1 times 500, I get 500. I take 0.5 times 1,000, I'll get 500, right? So the number, what are we actually doing here? Let's actually use factor label method system, and this is always a good way to check. So I take 1, oh, that was crazy, 1 mole. So this is equal to 1 mole per 1,000 milliliters, right? Its molarity is moles, sorry, per liter, or moles per 1,000 milliliters. Does everyone follow? I usually just in my head, like if because I always put 1 mole, and if I'm working with solutions that are in milliliters, I'll just put that as, I'll just do it in my head. And you're fine to do that, or you can do a conversion. But if I have a 1 molar solution, that's the same as 1 mole of that compound, whatever it is, over 1,000 milliliters of solvent, so it's in there. I'm going to multiply that by 500 milliliters of my compound. So this is just telling us kind of the density, right? The molar density, that's what molarity is, times the volume that we have it in. I have 0.5 moles if I solve for the left side. Now I'm going to do the other side, so I have 0.5 moles per 1,000 milliliters. That's the same, that's what 0.5 big M means. That big M means moles per liter. Multiply that by 1,000 milliliter. The milliliters cancel out. These numbers are the same. That's why this works. And it only works because these number of moles stay the same from the left to the right. I'm not pulling anything out of here and leaving some behind and then putting that in here. I am just, this is a dilution. So people will very frequently use this inappropriately. So if you're looking at your book, it might use V for volume and big M for moles, molarity. You can use this for other, it could be grams per milliliter. There's other options. So that's why a lot of times they'll use a C for concentration. It is the same kind of idea. As long as you're using the same type of units, or you can't change the units in there. So, all right, so let's use this idea. I want you to take a second. What volume in milliliters of a 16 molar H2SO4 acid must be used to prepare 1 liter of a 2 molar acid solution? So now we have to, this is a little different than how I presented that before. What is my initial concentration? We know everything except for V1. So that's where the trick of this is. You have to identify what is what. So we have 16 molar solution as the starting point. What volume of this solution must be used? So what is our starting volume? We don't know. And then we're going to make 1 liter of a 2 molar solution. So now I take this over here. I'm going to take this and divide it by this number so I can solve for V1. So we rearrange that. 2 molar times 1 liter divided by 6 molar, 16 molar, and that gives me, I basically just simplified this on top, right? 2 molars, remember moles, that big molarity is moles per liter, so I'm canceling out the liter units. That equals moles per liter. These liters will cancel out, and that's how I get that mole group. And then this molar is moles per liter, so that's how I get these. And then, I don't know, you guys know this little trick, this rule for algebra. If I have this in the denominator, so this liter comes up to the top, and then this mole stays out on the bottom. So these moles actually cancel out. So my unit's actually liters. If you have a fraction in a denominator, those things swap up. That's kind of an algebraic rule that people sometimes aren't sure about. Remember, so that in the bottom there, dividing by that number and that unit. Remember, we have to use units, have to follow the same algebraic steps. So that is why, because the units come out, you could do this all through factor label method system, but this is just an easy way if you know you're just doing a simple dilution that also works as well. So this was just to convert from liters to milliliters because I wanted this in liters. So this is just factor label system. 1,000 milliliters is 1 liter, and that's going to give us 125 milliliters.
Try this question using that technique, that tool that I just showed you, and post your answers in our Blackboard space.
If we have a balanced equation, right, we're breaking down these ions. And for every, if I break down sodium, it's a +1 ion. Carbonate is a -2. But to balance this out, because I have 2 of these on the left side, I need 2 of them on the right. Remember, we're only use coefficients. We're not going to put those in the subscript because it's not a molecule, it's an ion. You do the crisscross rule, figure that out. So I have 2 sodium ions and carbonate ion. I have, for every one of these that falls apart, I get 2 of these out. So it's that coefficient that I'm using to determine now the next steps for if I have a 1.0 0.150 molar solution, what are the concentrations of each of these ions? Here's my starting point. I have 0.150 moles of sodium carbonate over 1 liter of sodium carbonate. That's what molarity means. That's what the big M means. You have moles over liters. It's a constant. It's a density idea. So the reason I break that apart is so that I can use factor label method system with my units, so that I can create a flow to start canceling out other units. With this molecular equation I have, or ionic equation I have up here, I know that for every 1 mole of this sodium bicarbonate, right, I have that on the bottom in the denominator of that second part, so that I can cancel my moles of sodium carbonate. I have 1 mole of sodium in that solution. And now that's tricky though, right? Because I have still that liters of sodium bicarbonate. The thing is, right, that it's actually just water. This is really just water. It's not actually sodium bicarbonate. It's liquid water is the solvent. So that 2 moles of sodium ion is in that, it's really water. And so then I have moles over liters again. And so that gives me, if I take 0.150 times 2, I get 0.3 moles molar sodium solution. For carbonate, the same idea. We have it's the same. It's a 1-to-1 ratio between the carbonate and the sodium carbonate. There's just 1 in front of both of those compounds for the coefficients. So it's the same concentration. So usually when we're doing these kind of solutions, making these in an analytical lab, you would take something that you can use to deliver, right? We talked about pipettes or something that's good at delivering, maybe a burette. Pipettes are probably a little more practical generally. We're going to pull out at certain volume, and we're going to put it into a graduated or a volumetric flask. Excuse me. Volumetric flasks are great for mixing these compounds up. You bring that up with water to the volume you want at the end, and then you'd mix it up. So this is how we prepare specific solutions, and we talked about this in the classroom. So I just want you should envision this when we're thinking about that C1V1 equals C2 V2. What you pull up into this pipette is your initial volume, not what's in this bottle of everything, right? So if you're going to do these problems, you want to make sure you're looking at these properly. What's the volume of a 12.1 molar hydrochloric acid needed to create 250 milliliters of a 3.2 molar hydrochloric acid solution?
Please try this problem out and then post your answer in Blackboard.
So we have, we can use concentrations. This is kind of the important concept here, is that we can use these to determine the number of moles in a certain volume. And it's the same stoichiometric techniques that we discussed in chapter 3. So we have molarity versus moles. We can use the same kind of ideas there. Titration. So these concepts are used typically in analytical labs for quality control, and they can be helped to look at water quality or quality control in food industry or various other industries. Chemical industries use these as well to make sure that they know what their concentrations are of even their acids or bases or other kind of ions in their solutions. So we have to know what, in order to do a titration, to figure out exactly how much we have, we need to know what that chemical reaction is, what's happening. Usually it needs to happen quickly, so if you're going to drop something in a solution, you need to know it's going to happen very shortly, not in like 5 weeks. So there are different periods of time that some of these chemical reactions might happen in, and we need to know at least one part of, you're looking at a stoichiometric equation, you need to know the exact quantity at all times of at least one of those reactants. And then we can figure out using stoichiometry, since we know that complete chemical reaction, you can use that just one compound that you're analyzing to kind of figure out where everything else is at in that reaction. So a lot of times you'll do titrations. You probably have used like this phenol red indicators. So at certain pHs, those will turn on. So we do this sometimes in where you kind of drop a liquid in here and it's going to turn red if it's a really high pH, and then at neutral it might just start to turn pink, and then if it's super pink, you've gone past the point, you've actually gone past the median point. So this is just an example of titration. So if you're looking at orange juice, you want to figure out the the acid concentration, citric acid concentration. You'd use a base. So just like the chemical reaction, we know we have a strong base and an acid. It's the same. It's a metathesis reaction that's happening. And you would add a certain amount of that sodium hydroxide until you would neutralize all of the citric acid in that solution. And then once you start to add more sodium hydroxide, once all of this acid has been used up, then you're going to get a huge spike in what your pH is going to be. And so you need to know exactly what the concentration of that sodium hydroxide is, measure the volume that you drop in there, and then once that is depleted, then basically you can use that to know how much of the citric acid was in there. And usually for doing this in a lab, we're not going to do a titration this semester, but you would do that in other chemistry classes. But usually that's why we have the burettes. Those are typically used for titrations because you can dial in small drops in very small volumes to get your endpoint. And usually you'll use, at least so you can identify where your endpoint is, we have different compounds that will turn colors. And there's more calculations that need to happen to know where that color change is going to be. It's not always at neutral pH. So I've had students in the past in our analytical chemistry class, they just made the assumption that the pH had to be 7 for everything to be finalized, and that's not always the case depending on what you're working with. So we have different color indicators that change different colors at different pHs to kind of give you a warning that, hey, maybe you're getting close to your endpoint. But you basically use this to do that, and then you can figure out the exact volume you depleted, and then you can use the volume to determine the number of moles of the base you used, and then you can use the number of moles in the base with the stoichiometry of the reaction to figure out how much starting material you have. So I'm not going to ask, these are not going to be on your quiz or anything, but I did want to just know just some of the definitions. Some of the titrant is that solution in the burette, and the analyte is the solution you're trying to look at. So the citric acid, for example, would be the analyte, and the titrant would have been the sodium hydroxide. The equivalence point is when the moles of the titrant and the moles of the analyte are equal. That's not always going to be a pH of 7 because you might have other stuff in the orange juice. You might have other things that might be changing the pH a little bit. So that's the equivalence point is not always pH of 7, but that's commonly kind of confused. And an indicator is just a thing like a phenolphthalein that might turn something red or give you an idea that the endpoint is coming or near. And the endpoint is when both of those complete the reaction, typically come to an equivalence point. Okay, so I just wanted to look at this idea of using stoichiometry to figure out this kind of question here. So how many milliliters of a 0.0475 molar H3PO4, so phosphoric acid, could be completely neutralized by 45 milliliters of a 0.1 molar potassium hydroxide solution? So I've balanced this equation for you already. Remember, we used something we know. What do we know? What do we have all the information we need to know about? We don't know how many milliliters of this H3PO4 are there. But we do know 45 milliliters of a 0.1 molar potassium hydroxide solution. This is what we do know. So if I have a volume and I have a molarity, I can find the number of moles I have in there, right? So the first step is determine the number of moles of potassium hydroxide. And then we can use the stoichiometry of this balanced equation to figure out how many moles of this H3PO4. Then we'll have the moles, but we don't have the milliliters, but we do have a concentration of H3PO4, and then we can use the moles and the concentration to figure out the volume.
Please take some time to work through this, try to solve the problem, and post in our Blackboard space.
We have a HNO3 titrated with 75 mils of calcium hydroxide. What's the concentration of HNO3 in the initial sample? So we want to run the reaction, do the metathesis. It's an acid-base reaction. The reaction should go. It should make water.
I'd like you to give this a shot first, maybe pause here and try to run this. If you're not sure, I'm going to go through the solution next.
In order to solve this question, we need to start and look at what we have. And again, we have this nitric acid, HNO3. We have 25 mil sample. So we need to start with looking at how many moles of that are in this sample. And we don't know the concentration of this, so we need to look at the calcium hydroxide, which we're titrating it with. We have a 1.3 molar solution. We have 75 milliliters of that. So I'm going to start with the 75 milliliters, and I'm going to convert this to liters because I know that this molarity of the calcium hydroxide is in moles over liters. And this will allow me to figure out how many moles of the calcium hydroxide, right? So once I multiply the 0.75 liters times this ratio of 1.3 moles over liters, the liters are going to cancel out, and I'm left with moles of calcium hydroxide. Next, I need to use the stoichiometry of the equation, this 2-to-1 ratio, 2 moles of the nitric acid versus the calcium hydroxide, which we just need 1 mole. And that's going to be here, and that's going to allow me to convert from the calcium hydroxide unit to the nitric acid units. So that 2-to-1 ratio tells us that we are now in moles of nitric acid. So then I solve this, and I'll get 1.95 moles of nitric acid. That's not what I'm asking for. I'm asking for the concentration of the initial sample. So I know how many moles there are, and I know the initial sample volume, so I should just be able to take this and divide it by the volume. Now, this is in milliliters, and I know that molarity is in moles over liters, so I need to convert this again. I have 1.95 moles of the nitric acid, and I converted it to 0.025 liters, and that gives me my final answer when I do that division. Notice the moles over liters will be now molarity. And that concludes our discussion on titrations and the types of reactions that we're going to do in chemistry lab space.